Hello. We will now continue with our study of heat energy by discussing more about condensation and evaporation. We talked about these phenomenon before, is that right? What is evaporation? Evaporation is the phase change from liquid to vapor. Condensation is the phase change from vapor to liquid, a process that continuously happens in nature. Now, consider a quantity of water in a container like this. I have a quantity of water in a container. Now, as heat is supplied to this water, what will happen? The molecules will gain energy and they will start moving faster. Now, some molecules of water that have a higher than average speeds. Now, you cannot expect that all molecules in a body of water will have the same speed. Some molecules will have greater speed than others. Now, when those molecules which have a higher than average speed come and hit the surface, they will simply escape on the surface or escape to the space outside. That means the molecules from the liquid state become the vapor, and that is evaporation. Well, a molecule here gets more than average speed, it can simply escape. Now, the latent heat needed for evaporation. Now, remember, in order that a liquid molecules may change into vapor, the molecules need to be supplied with potential energy because they need to break the molecular forces that hold them together in the liquid so that they can escape. Now, where does the molecule get the potential energy from? Well, the latent heat needed for evaporation is absorbed from the water body, and as a result, you see, because these molecules that escape have greater than average kinetic energy, and when they escape, the potential energy needed to escape is actually taken from the liquid body. That means the speeds of the remaining molecules will actually slow down. The body of water therefore will cool down. Evaporation actually causes cooling. Try and collect water in your bath, say on a morning, and try taking a bath in that water in the evening. That water will be fairly cold. Now, the temperature, the coldness actually happened because of evaporation. Evaporation produces cooling. Now, there is always water vapor above the surface. Now, this body of water in this liquid has always water vapor above it. Now, that means evaporation and condensation always happens at all temperatures. Now, some vapor molecules, when colliding with the surface of water, will return to the water state. Now, here we have a molecule of vapor. You see, molecules of vapor will be in a continuous state of motion. And suppose one molecule while moving comes and hits the surface, it can then return to the surface. So evaporation and condensation happens actually at all temperatures. And while evaporation takes place, heat is absorbed from the liquid body. While when condensation takes place, what happens? When a molecule returns to the liquid or to the liquid state, the additional potential energy it has needs to be given off. That means condensation will produce warming. Well, During condensation, latent heat is released. During evaporation, latent heat is absorbed from the body. And during condensation, what happens? The extra heat is released, warming of the surroundings. So condensation always produces warming of surrounding because heat is released to the surrounding. Now, when the number of molecules escaping the liquid surface equal to the number of molecules returning to the water, we say that there is equilibrium between water and vapor. Now, when there is equilibrium between this water and the vapor on its top, the number of molecules escaping from the liquid to become vapor will be equal to the number of molecules returning from vapor to liquid. Now that is what we call equilibrium between liquid and vapor. Now evaporation and condensation happens at all temperatures. But if you supply heat, evaporation will dominate, and if you cool down the air, condensation will dominate. Now, can you explain why evaporation causes cooling and condensation produces warming? Well, here again, you can earn one extra credit point by writing a paragraph on how evaporation causes cooling and condensation produces warming. Just one sentence is not enough. You got to explain to me what you really understand by that and give examples of your experience. Have you ever experienced evaporation causes cooling? Well, I'm sure you have, so you got to quote those examples. Now, the speeds of water molecules determine condensation and evaporation rates. What does that mean? It means if the speeds of molecules in a liquid are greater, or when you supply heat to a liquid, if you heat a liquid, the speeds of molecules will increase, which means evaporation will dominate. On the other hand, if you keep a parcel of air which contains water molecules, that molecules will condense to form water. So whether evaporation dominates or condensation dominates depends on the temperature, the speeds of the molecules. Now, the temperature of the air, the amount of water vapor in the air, and the surface of liquid, they all determine whether condensation or evaporation dominates. Now, if there is too much water vapor in the atmosphere, in the air, then it will be very difficult for molecules to get out into the air because the air is almost saturated with water vapor. Now, if the air is dry, the evaporation will be very fast. You see, that's the reason why on a dry day, when there is very little humidity, you feel cold. Whereas on a humid day, you feel warm. Why? Because on a humid day, the sweat from your body will not evaporate. The air has lots of water vapor, therefore the sweat from your body will not evaporate. You see, if sweat from your body do not evaporate, you feel very uncomfortable. You see, it is nature's way to cool our body down by evaporating our sweat. When the sweat evaporates, the latent heat for that evaporation is absorbed from our body. That will cool down the body. So when the atmosphere is saturated with water vapor, you feel very uncomfortable or you feel very sticky and hot because evaporation from your body will not happen. Well, under normal conditions, evaporation and condensation rates are equal. In other words, again, going back to my examples, under normal conditions, the number of molecules leaving the liquid to become vapor and the number of molecules returning from vapor to liquid will be equal. There will be equilibrium. Now, this is the normal state. The number of molecules leaving the liquid to become vapor is the same as the number of molecules of vapor returning to the liquid. So this is the situation of equilibrium between liquid and vapor. On the other hand, if you cool the air parcel, now if the temperature of the air is now reduced, what happens when you reduce the temperature of air? When you reduce the temperature of the air, the molecules, the vapor molecules will slow down. And when the vapor molecule slows down, they condenses back to liquid. So when the parcel of air is cooled down, condensation will dominate. In other words, there you are. When the parcel of air is cooled down, more number of vapor molecules will come back to liquid, and only a very few liquid molecule will go to vapor. That means when the air is cooled, the condensation will dominate. Now, this is the reason why clouds are formed. For example, in this room, there is certain amount of water vapor. If I can cool this room down by turning down the AC, a time will come when I will see the windows, the glass windows will all begin to fog. Why? Because when the temperature is cooled down, the water vapor will begin to condense. It is the condensed water vapor that is fog and cloud and so on. Now, many more of the water molecules become slow enough to change back into liquid. That's what happens, and that is the process of condensation. On the other hand, if you warm the air parcel, what will happen? If you increase the temperature of the air parcel, the air molecules will speed. That means more water vapor can be accommodated in that air. When the temperature increases, a space can accommodate more water vapor. That means the rate of evaporation will increase. So when the temperature is increased, evaporation will dominate. Look at this diagram. When the air parcel is warmed, more molecules will escape from the liquid to become vapor than the number of molecules condensing to become liquid. So the temperature of the air actually determines the rate, whether the rate of condensation or the rate of evaporation will dominate. Now, many more molecules in the liquid will actually are fast enough now to evaporate. More molecules will leave the liquid than the ones that return. Now let us talk about a very important concept that everybody knows: relative humidity. What is relative humidity means? Now you know that when the relative humidity is high, you feel sticky and hot. The air will be almost saturated with water vapor. What is the meaning that the air is saturated? You see, at a given temperature, a certain space can only accommodate a certain amount of water vapor. Now, if you put in more water vapor than it can accommodate, water vapor will condense to form water. So, when a space contains the maximum amount of water vapor, that space is said to be saturated with water vapor. Now, how can you change the state of saturation? Well, you can actually change the state to saturation by increasing the temperature. If you increase the temperature, the ability of the space to contain water vapor will also increase. At a higher temperature, more amount of water vapor can be contained in a given space. If you reduce the temperature, the ability of a space to contain water vapor will become less. And that's the reason why when you reduce the temperature, the water vapor will condense to form water. Alright. Now, warm air can hold more water vapor than cool air. Why? Because warm air, the molecules will be faster. Cool air, the molecules slows down, they will condense to become water. So warm air can actually hold more water vapor than cold air. As the air temperature decreases, the ability of a given space to hold water vapor decreases. As I told you, if I decrease the temperature of this room, what will happen eventually? This space will become saturated. That means at that particular temperature, this space will not be able to hold any more water vapor. Now, if I further reduce the temperature, the water molecules will begin to condense to form water. Fog will begin to form. If a given space cannot hold any more water vapor, that space is said to be saturated. Now, if the temperature of a saturated space is decreased, now if the space is saturated, and if you now decrease the temperature further, then condensation will happen. Now, what is the definition of relative humidity? Now, what's this definition? Relative humidity is the ratio of the amount of water vapor that is actually present in a given space to the amount of water vapor that will saturate that space at that temperature. Well, what is the meaning of a ratio? A ratio is one quantity divided by another quantity. Now here, what are the two quantities? The first quantity is the amount of water vapor actually present in a given space. Now, what is the second quantity? The amount of water vapor needed to saturate that space at that temperature. For example, in this room is not saturated. You can see I'm wearing a jacket. I'm not feeling warm or I'm not feeling sticky or hot. I'm feeling comfortable. The space is fairly dry. But does that mean that there is no water vapor here? There is water vapor, but the space is not saturated. The space can take much more water vapor. So, if I want to find the relative humidity now, what I can do is, I can measure the amount, I can measure the mass of water vapor in this room now. Alright? I'm going to measure it. I'm going to write it down on the white screen. Alright? I'll be back in 30 seconds. I'm going to measure the mass of water vapor in this room. Don't ask me how I do it, but I know how to do it. Okay, I'm going to measure that, and I'm going to say the mass of water vapor actually present. The mass of water vapor actually present, well, I got it as 120 grams. Alright, what that means is, at the moment, this room contains 120 grams of water vapor. Now I need to know how much water vapor is needed to saturate the space. Well, that's a little difficult thing for me. I'm going to make an assumption. Suppose I need 100, well, give me a number. Well, suppose I need 200 grams to saturate this space. Alright? So the mass needed to saturate, the mass of water vapor needed to saturate the same space is 200 grams. And so, can you calculate the relative humidity of this room from these two figures? The mass of water vapor actually this room now has is 120 grams. And the mass of water vapor that will saturate this space at this present temperature is 200 grams. Therefore, relative humidity, watch it again. Relative humidity is the ratio of the amount of water vapor actually present in the air, and that is 120 grams, to the amount of water vapor that will saturate the same space at the same temperature. So, I can calculate the relative humidity as, look at this, I'm going to say, watch the top right hand corner of the screen. Relative humidity equal to mass of water vapor actually present is 120 grams divided by the mass of water vapor that will saturate the space is 200 grams, and if you multiply that by 100, give me the relative humidity in percent. Can you tell me what this is? Isn't this 60%? Yes. So that tells me the relative humidity in this room now is 60%, a very comfortable value. Alright, let me write down the equation for you for relative humidity. Now this is the equation we will use to calculate relative humidity. Relative humidity equal to amount of water vapor actually in air divided by the amount that will saturate the same space at that temperature and multiply that by 100 to make it a percent. Alright, let me give you an example. We did one example, another example. If a given space of air contains 50 grams of water vapor, and if 60 grams of water vapor will saturate that space at the same temperature, then what is the relative humidity? Relative humidity is 50 grams divided by 60 grams multiplied by 100. That is 83% is the relative humidity of that space. Okay. The temperature at which a given space becomes saturated is called the dew point of that space. You see, if you decrease the temperature, I told you, if I decrease the temperature of this room, the space will get more and more saturated. And a time will come at a particular temperature, the amount of water vapor that is now present will saturate the space. And that temperature is what we call dew point. Why do we call it dew point? Because if you reduce the temperature any further, condensation will happen, and that is how dew is formed. Is that right? Dew is the result of condensation. Now, a measure of the temperature and the dew point at a place is enough to calculate the relative humidity. Now, actually, if you can measure the dew point, there are charts that will give you the relative humidity corresponding to that dew point. Alright, actually it is very simple to measure the dew point. I'll give you a simple experiment that you can do. If you take a little volatile liquid, you see, volatile liquid is a liquid that evaporates very fast. Ether, have you heard of that? Ether, a spirit that doctors and nurses uses to clean the wound. Now, that is a very volatile substance. A volatile substance is something that evaporates very fast. You know that something that evaporates very fast will take away a lot of heat from your body. If you put spirit on your hand You feel cold. Why? Because that spirit will evaporate, taking away heat from your body. You see? So, if you take some spirit like that in a small container, put a straw in it and blow. Now, blowing will further accelerate the rate of evaporation. You can see at a certain time, the outside of the beaker will begin to fog. That means dew begins to form. And if you measure that temperature, that will be the dew point. And if you know the dew point at a place, you can refer to a chart, and that will give you the relative humidity of that place. So if the dew point is close to the air temperature, what do you think? Now, if the dew point is very close to the room temperature, will the room be more saturated or less saturated? Now remember, dew point is the temperature at which a given space gets saturated. So if dew point is very close to the room temperature, it means the relative humidity is very high. That means you feel very uncomfortable. If the weatherman says that the dew point is very low, it means the air is very dry. If the dew point is high, very close to the room temperature, it means the air is almost saturated with water vapor. Tell me, why do we feel sticky and hot when the relative humidity is high? You want to write a small paragraph on that? Anything you send me will earn you an extra credit point. Now remember, when you make an effort to learn, you will be rewarded for it. Okay. Our body temperature is regulated by evaporation from our skin. The energy needed for evaporation is absorbed from the body, cooling the body down. You see, when you stand outside, I know most of you experienced this. You jump into the pool and come out. If it is windy, you feel very cold. Why? Because if it is windy, the evaporation will be faster. The water will evaporate from your body very fast, taking away heat from your body. The potential energy needed for water to become vapor is absorbed from your body. The latent heat is absorbed from your body. So you cool down and you feel cold. Alright. If the outside air is nearly saturated, very little evaporation takes place and very little heat is removed from your body. That means you feel sticky and hot. Let's now talk about transfer of heat. How do heat get transferred from one place to another? What are some of the mechanisms of transfer of heat? Well, thermal energy is transferred from one place to another by three main mechanisms. They're called conduction, convection, and radiation. Now, what are these processes? What is conduction? Well, it's a very simple process. Conduction is a mode of transfer, a mode of heat transfer within an object due to interaction between atoms and molecules without involving their bodily motion. In other words, when you heat one part of an object, the molecules will begin to vibrate faster, and that faster vibration gets passed on from molecule to molecule so that heat reaches the other part of the object. This is an aluminum rod. If I heat one end of it, heat will transfer from one end to the other by molecular vibrations being transferred from molecule to molecule or atom to atom. This method of heat transfer is what we call conduction. Now, conduction in metals is specially assisted by the motion of electrons which carry thermal energy from one part of the conductor to another. Now, metals like aluminum, the conduction is much more complicated than simply heat getting transferred from molecule to molecule, because there are free electrons which also play a considerable role in transferring heat from one place to another. We will not go into the details of it. Now, as energy is passed on from one molecule to another or from atom to atom, heat travels progressively from one end of the conductor to the other. That is conduction. Now, if I take an example in a classroom, suppose I have 100 students in the classroom and I want to distribute a box of chocolate. What do? I can do it in many ways. I can take one chocolate and give it to the first student. That student will pass it on to the next, until that chocolate reaches the last student. Now, this is the mechanism of conduction. Heat received by the first molecule will transfer it to the next, and to the next, and to the next, until it reaches the very last molecule. Alright. A spoon in a cup of hot soup becomes warmer because of the heat from the soup is conducted along the spoon. Now, I know most of you are familiar with it. We all know that metals are good conductors of heat. Is that right? Yes. Now, conduction is most effective in solids, but it can happen in fluids as well. Now, why is it that conduction is most effective in solids? Because it is in solids that the molecules are held on together, so that what one molecule does easily gets passed on to another molecule. Whereas in liquids and gases especially, there is not much contact between molecules. Molecules are so free. So there is no guarantee that when one molecule receives more heat, it gets transferred to the others, because there is no intermolecular forces. You see? So solids are better conductors than liquids or gases. Now, have you ever noticed that metals tend to feel cold? Now, see, even now, when I touch this aluminum rod, my hand actually feels cold. You see? Try that on your arm. Now, is it because the temperature of this aluminum rod is cooler than the remaining, outside temperature? Now, for example, if I touch this wood, I don't feel as much as I feel cold with the aluminum. Now, why do we feel cold? You see, metals are good conductors. So when I touch a metal, heat from my hand, you see, our hand or human body is warmer than the surrounding temperature. So when I touch the aluminum rod, heat from my hand is conducted away by aluminum much faster than wood will do. Wood is a bad conductor. Aluminum is a good conductor. It means it can remove heat from my hand much more efficiently than wood does. So that makes my hand feel cold, because the heat from my hand gets removed faster, not because aluminum is cold. All right. Now, they only feel colder because they conduct heat away from your hand. Now, you perceive that the heat is leaving your hand. When heat leaves your hand, you feel cold. Just like when sweat evaporates, you feel cold. So when sweat evaporates, it carries away heat from your body. When heat leaves your body, you feel cold. Now we have large numbers of good conductors and bad conductors of heat around us. And both these materials are useful to us, is that right? We are able to cook our food effectively because we have good conductors. They make good cooking pots. Whereas we have bad conductors so that we can have a good handle. We will not burn our hands. So good conductors and bad conductors are equally useful for us. Alright, let's now talk about convection. What is the mode of convection? Now let's go back to my chocolate example. I told you one method of distributing the chocolate. That is, I gave one chocolate to the first student, and that student passed it on until it reached the last student. And this is like conduction. Now I can also distribute the chocolate by asking each student, come over, pick one chocolate and go back to your place. You see that? Every student comes, picks a chocolate and goes back. Now this is what happens in convection. Convection causes a convection current. What is a current? A current is a flow. When students move in and pick a chocolate and go back, I have a current of students flowing in the class. In the same way, have you noticed when air at a certain place is heated, that hot air will rise and cold air will sink? You see, cold air will come to receive heat and then move away. More cold air will come, receive heat and go away. This is called convection current. So, convection is the transfer of heat by the actual movement of the matter. You see, cold molecules will move in to receive heat and move away. The actual movement, or it causes a current, a flow. Heat leaves the coffee cup as the current. Now here, the air immediately above the coffee cup becomes warm, and that warm air will rise. You can see there is convection there. Convection is the transfer of heat energy in a gas or a liquid. Now, why can't convection take place in a solid? Can you tell me? Why can't convection take place in a solid? I said convection takes place only in gases and liquids. You see, convection can happen only if molecules can move from one place to another. In a solid, the molecules are fixed to their relative positions. So, a solid cannot convect. Only a liquid or a gas can have convection current inside of it. Now, convection is responsible for making water rise and fall when you heat a pot of water. Have you actually seen when you put a pot of water for heating? If you look at it carefully, water from the bottom will rise and water from the top will sink. And this process will keep on until the water boils. And if you watch it boils, it's a great big commotion, motion of molecules. Molecules moving from one place to another. Warm molecules moving away and cold molecules coming to take its place. And that happens continuously, setting up a convection current. So the warmer portions of the water are less dense and therefore they rise. When air is heated, it becomes less dense, and when it is less dense, it will rise. Same way with water. When water is heated, it becomes less dense, and it will rise. Now, meanwhile, the cooler portions of the water will sink and come down to receive heat. Land and sea breeze are examples of convection currents that take place in the air. What are land and sea breeze? Now, we talked about specific heat, didn't we? Now, which has greater specific heat, water or soil? You know that water has a very high specific heat. What does that mean? In order to heat water by 1 degree, you need large amount of heat. Whereas, in order to heat land by 1 degree, you don't need that much of heat. Therefore, tell me, during the morning when sun comes up, the heat from the sun falls on the sea as well as on the land. So, tell me which of them will get heated faster? Because the specific heat of water is very high, water will take a very long time to warm up. Whereas land will become hot very fast. So, what happens? The air above land will become hot and the hot air will rise. Now, the air above sea is still cold, and that cold air will move in the place which is vacated by this rising air. So look at this, warm air from the land will rise, cold air from the sea will move in. That is called the sea breeze. Now look at this one now. Now this is land. Now during the day, the land gets hot much faster than the sea. So the air above land rises because this is hot, and the cold air from the sea will come in to take its place. And look at the flow of air. You see, this is an example of convection current, and this is called a sea breeze. Now, this is during the day. Now, once the sun goes down, the sea begins to cool down, the land also begins to cool down. Alright, tell me, which of them will cool down faster? Which of them will lose heat faster? Well, again, it depends on the specific heat, because the sea, the water has a greater specific heat. Water cools down very slowly, whereas the land will cool down very fast. So in the evening, the land will cool down faster, the air above the sea will remain warm, and that warm air will rise, and the cold air from the land will come in to take its place. Now there you have the land breeze. So the sea breeze and the land breeze are good examples of convection currents in nature. In fact, some of the wind patterns that we have are also caused by this phenomenon. Actually, different parts of the surface of the earth gets heated differently. That means the parts which are very hot, the air will rise, and cold air from other regions will rush in. Is that right? When there is a low pressure is created by rising of the warm air. And into that low pressure, air from other sides will rush in, creating a wind. So all these phenomena are actually convection currents. Now, what are some applications of convection? Now, we talked about this. The water in a pot gets heated uniformly due to convection currents. Hot regions will rise and cold regions will sink. Alright? Another example. Now, a heater inside a room, the heater sits at one corner, and that can actually heat the entire room almost uniformly. How? The air immediately in contact with the heater is warm and less dense. It will rise, and cold air will sink, coming down to get heated, and that creates a convection current in the room. So there is a continuously warm air rising, cold air sinking. That will heat up the room uniformly with time. Now, another example is the supply of water for cooling your engine. This is actually a forced convection. Now, the warm water, after receiving all the heat from the engine, is warm. It goes to the top of the radiator, and it goes through the radiator. Radiator will allow the heat to escape, and the water cools down and it returns. You see, the warm water rises, the cold water sinks, and you have a convection current cooling your car engine. Alright, look at the refrigerator. Have you ever noticed where does the cold air come into your refrigerator? Does it come at the lower compartment or at the upper compartment? Well, this is where the cold air is, and the cold air is denser, so that will sink and warm air will rise. So the sinking of the cold air and the rising of the warm air will cool the inside of the fridge uniformly. So you can see these various phenomena are so much useful to us. The applications of conduction and convection are things that make our life easier for us. Alright, the third type of heat transfer is the heat radiation. Radiation. Let me go back to my chocolate example. There is a third way I can distribute my chocolate to my students. Can you tell me what that third way is? Well, I can take the whole chocolate in my hand, pick one and say, Thomas, catch. Come on, Rachel, catch. Is that right? I can pick one and throw it at you. And that is an effective way of distributing that chocolate. Now, radiation is a similar phenomenon. So, radiation involves the transportation of heat through empty space. I can just throw it. I don't need any medium. My throwing only involves the person who receives it and the person who throws it. So this is called radiant energy. In fact, all the energy that we get from the sun, come to us as radiant energy. Now, when you heat a cup of tea in a microwave oven, the water is heated directly by microwave radiation, a form of electromagnetic energy. Now, do you remember we talked about electromagnetic radiations? Electromagnetic radiations are radiations that differ widely in the wavelength and frequency. Now, do you remember some of the names of those? It is good to remember because we are going to use them in our next section. You see, electromagnetic radiations, the long waves are called radio waves. And as the wavelength becomes smaller, it becomes microwaves, and then infrared, visible light, ultraviolet, X-rays, gamma rays. They are all radiant energy. Energy that comes to us in the form of radiations, and we call it electromagnetic radiation. Heat is a form of electromagnetic radiations. Heat radiations are called infrared radiations. You see, heat radiations are longer waves than visible light. Transfer of heat by radiation travels at the speed of light and goes great distances even in vacuum. One of the most important characteristics of electromagnetic radiations is all of them will travel with the same speed in vacuum. In other words, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, all of them will travel with the same speed. Well, we talked about that, didn't we? Yes, we did. Now, do you remember this wave equation? We talked about this V equal to F lambda. F is the frequency, lambda is the wavelength, V is the wave speed. Now, wavelength and frequency can change. When the wavelength is very long, frequency is very small. If you multiply the two, for all electromagnetic radiations, if you multiply the two, they will be the same. Well, that means they all travel with the same speed. So what is heat radiations called? Heat radiations are called infrared radiations. All right. Now here I have an illustration of conduction, convection and radiation. Now watch carefully. First let's illustrate conduction. Now this is a metal strip and these are atoms of the metal. I'm going to start heating one end, and when I heat it, atoms will look red. Alright, and see how the conduction actually takes place. I'm going to heat it. Now watch carefully, it doesn't stay for a long time. You can see it starts heating and the heat travels right through the conductor, and that is the process of conduction. And how about convection? Now the man is sitting in front of the heater and you can see the air there gets hot, become less denser, it rises. Now it cools down after giving up its heat to other molecules. The cold molecules comes up, receives heat, and this is the convection current. Alright, so conduction and convection, and we have also a good example of radiation. This time heat is thrown by the heater, so it doesn't need any intervening medium. So these are examples of conduction, convection and radiation, and we actually experience that on every day of our life, don't we? Yeah. And finally, I have one more illustration of the phenomenon of convection and radiation. If you know how the heating system of a house works. Now this is not very common in Florida, but if you go to north, the heating system is very similar to this. You have a heat source which actually uses gas to heat water, and the hot water will circulate and the cold water will go up to receive heat, and you have actually a pump system that will allow that to happen. But a convection alone will make the circulation possible. The hot water is less denser, it will sink. When it gives off heat, cold water will go back and receive heat and it will circulate. And have you seen this kind of heating? There are tubes that run down the floor that takes up the heat. That means the floorboard gets heated and the heat is radiated out into the room. That's the radiant zone. That is a very common way of heating now these days. Well, rather expensive houses. The tube network, the hot water is allowed to flow through a kind of plastic tubes. Now the heat is actually absorbed by the panel above and radiated into the room. That's a very efficient way of heating rooms. Well, we have now talked about energy. That was the theme of our Unit 2. We talked about energy in general and then heat energy in particular in this lesson. Well, I'm sure now you are ready for your second test. Alright, so look through the practice test. Above all, make sure after you watch a lecture, always go back and do your homework and get back to me if you need help. Alright, then go through the practice test and then do your test before the due date. Okay, I wish you all the best. I will see you for Unit 3 later on.